Okay. Yeah. Great. Thanks. And looking how much, so I don't keep you all night. Yeah. So that was a great talk. Yeah. Thank you. That was a great talk. We heard about stars, what happens to stars at the end of their lives, and the cinders that are left. And I love learning how stars live, how stars die. But once in a while in astronomy, you can use stars to test something universal, something about physics itself, not about stars. And that's what I'm going to talk about here. I'm going to talk about how we are using one of those cinders, one of those neutron stars that we talked about, to test how gravity works. And that's pretty fundamental. Gravity is a pretty essential part of our lives. And this is joint work of mine and Nina Kusinskaya and Jason Hessels are at University of Amsterdam, and the rest of these folks are from all over the world. And I'd like to say, please feel free to put your hand up and ask questions, because I'd rather answer the questions you do have than the questions I thought you would have when I was putting this together at home. So please put your hand up. And I think maybe you were too clear to get many questions during it, so I'll try to be less clear. If you would like, if you would like more information about this, we did publish a paper. It's in Nature, so it's sort of meant to be accessible to scientists who aren't astronomers. But if you would like less information, we also did a YouTube video, which is actually does a pretty good job of explaining it in 5 minutes. I was very pleased. We worked with a local Dutch animator, and he did a lovely job. So, what do I mean by testing gravity? What is there to know about gravity? Well, our idea of how gravity works has evolved over time. Aristotle was a Greek philosopher, scientist, not really a distinction back then. And his idea of how gravity worked was that every object had a natural place it wanted to be, and that objects fell towards where they were supposed to be. So smoke went upward because it was supposed to be in the heavens, rocks went downward because they were supposed to be on the ground, they sank because they were supposed to be under the ocean. And in his theory, heavier objects were supposed to fall faster than lighter objects. If you dropped a big rock and a little rock, the big rock would fall faster, I guess because it was supposed to be further down. I don't know. This is obviously not actually how things work, but Aristotle didn't believe in experiment. His whole school of thought didn't believe that. They thought thinking about things was how you figured stuff out, not experiment. And so this idea of gravity hung on for a couple thousand years almost. Galileo started thinking about this, and still somewhat in the school of thought of Aristotle, he questioned it for logical reasons. He thought this didn't really make sense. He wasn't the first, but he thought it didn't make sense. There's a story about Galileo dropping things off the Leaning Tower of Pisa. We think he didn't actually do that. But the early Dutch physicist, Simon Stevin, actually did drop cannonballs off the Nieuwe Kerk in Delft. And sure enough, Aristotle was wrong, and Galileo was right, and he wrote back to his patron, Aristotle was wrong, exclamation point, which I think it took a lot to get an exclamation point back in the Renaissance. But so this meant people had to rethink how gravity worked. And it was experiment. It wasn't that we thought this was a nice theory and then we actually checked, and that's how things fall. And when they finally got to the moon, this is the astronaut Dave Scott, one of the later moon missions. He wasn't the first guy. I wanted to sort of thank Galileo and these early scientists for developing ideas of gravity. That's how they could get there. So he did this lovely demonstration where he dropped a hammer and a feather in the vacuum of the moon, and they fell exactly the same way in the gravity of the moon. They hit the ground together. This is a painting. They did not bring little portable HD video cameras to the moon in 1969 or whatever year it was. So there is a video on YouTube. I recommend watching it, but it's not fantastic quality. So, these are just descriptions. Things fall the same way. When Newton put together his theory of gravity, he actually had a theory that described how things moved. And it was remarkable, first because it was the first really mathematical theory. He actually had to invent the mathematics to make it work. You can thank him for calculus, if that's how you feel about calculus. But it was also the first theory that said that celestial objects followed the same rules as terrestrial objects. You think, okay, well, rocks fall, balls roll, but the things in the sky were just dots that, who knew how they worked? Newton's idea was that actually they worked the same way as everything on Earth. That was remarkable. But that's a side point. Newton built into his theory the idea that everything falls the same way. It doesn't matter what it's made of, doesn't matter how massive it is, they all fall the same way. This is Galileo's result, made an important part of Newton's theory. And I'm sorry, I tried not to get into too much math, but I think many of you will have seen at least this much before. Newton's theory says that if you apply a force to an object, it accelerates. And how much it accelerates? Well, the force is equal to ma. There's a mass that says how hard it is to accelerate an object. And I've put a little I, because that's inertia. That's how hard it is to accelerate an object. The other side of Newton's theory, at least when it comes to gravity, is that the force between two objects is some big G times the mass of one object times the mass of the other. And here, the mass is how much it likes gravity, how much gravity likes it, how much it interacts with gravity. So I've put a G on this one. This is the gravitational mass of these objects. Now, I see some of you giving me funny looks, because normally we don't talk about inertial mass and gravitational mass. Because if every object falls exactly the same way, that means that for every object, gravitational and inertial mass are exactly the same. So we don't bother keeping separate ideas. But that's not something that's automatically true. It's something you have to test with experiments. So Newton actually built some pendulums made up of different things, and he tested them, and it didn't matter what they were made of. So Newton built that into his theory. So when Einstein came along and needed a better theory of gravity, well, he said, okay, if every object falls the same way, if it doesn't matter what something's made of, if there's no other special feature of objects, maybe gravity isn't really a force at all. Maybe when things are falling, maybe they're just kind of sliding through space according to some rule that has nothing to do with what they are. Maybe it's just the geometry of space-time that makes objects fall. And he built a whole theory on it. There's all kinds of interesting stuff that happens in it as a result of this idea that gravity is geometry. But that only works if all objects fall the same way. If it matters what they're made of, then that can't be geometry. So this idea, that all objects fall the same way, is key to Einstein's theory. And Einstein's theory has done a good job of predicting the solar system, but people are still a little bit uncertain of it. There are some limits. We think something else takes over at some point. So this question, do all objects really fall the same way, is something we should look into. Well, you can ask, does it matter what it's made of? That's something you can test in a laboratory. You can put lumps of uranium and lumps of copper in a very delicate torsion balance. You can put it on a very smooth turntable, and you can measure the gravitational pull of a nearby hill on your test objects. And there's a group at the University of Washington that does this. And they do these incredibly, incredibly delicate comparison experiments, and they can say that actually copper and uranium are attracted the same way by gravity at the sort of 10 to the minus 13 level. That's, they do the calculation, they agree to 13 decimal places. These are these fantastically delicate experiments. It's amazing what these people can do in a laboratory. But that only handles composition. What if your object, well, gravity is a bit special, because objects have gravity. What Einstein says is that actually even gravity works that way. Even gravity doesn't affect things. That gravitational and inertial mass are the same concept, even if your object has really strong gravity inside it. You might think, why wouldn't it? What makes gravity special in this? Well, in order to make, one of the things that Einstein's theory did was it predicted the orbit of Mercury better than Newton's theory ever could. And to make that work, whether Einstein was right or not, to make the orbit of Mercury work, you need gravity to have nonlinear superposition. In other words, if you take two objects, you put them together, the gravitational pull of the together object is not the sum of the gravitational pulls of the objects when they were separate. the binding energy that holds them together has to have mass. Now, if that sounds like I'm saying gravity has mass, gravity produces more gravity, that is what I'm saying, and yes, it is weird, and it kind of makes your head hurt, and it leads to black holes, and is very troubling. So we would like it not to be true, but unfortunately, to make the orbit of Mercury work out, whether Einstein was right or not, you need this nonlinear combination effect. And if you have a nonlinear combination effect like that, it's kind of a miracle if it works out that very massive objects who have this binding energy should fall the same way as not very massive objects. You should expect them to behave differently. You should expect the gravitational binding energy holding them together to fall differently from all other kinds. And it's kind of a miracle that in Einstein's theory, they fall exactly the same way, even if it's gravity holding them together. And that miracle doesn't happen if you change Einstein's theory a little bit in any direction, almost any direction, that miracle falls apart. It stops working. So this is somewhere where Einstein's theory satisfies this, and almost every deviation from it fails. So we would love to ask, does gravity fall the same way as everything else does? Do objects with extreme gravity holding them together fall the same way as objects without extreme gravity holding them together? That would be a fantastic question to test how gravity works, if we could ask it. Now, how do you go about asking such a question? Well, I mean, you could try a laboratory experiment where you start dropping objects, but you can't build a laboratory object that's held together by gravity. They have to be sort of planet-sized or bigger. So how do you do this? Well, you've got to have some astrophysical thing where they're moving around under gravity and they're falling. And, orbits are falling. So you can have some things orbiting some other things and ask whether the falling objects fall the same way. So, for example, when Dave Scott and his colleagues, oh my God, this is terrible. When Dave Scott and his colleagues went to the moon, they left some instruments. And one of the things they left was a big set of mirrors. And people on Earth can now fire giant space lasers at the moon and get reflections back from those mirrors. And they can measure the distance to the moon to the nearest centimeter. They've been doing this for 35 years. So there's 35 years of giant space lasers measuring the distance to the moon to the nearest centimeter. And so they've got a super accurate picture of exactly how the moon orbits the Earth. And of course, we're all going around the sun, so both the Earth and the moon are falling towards the sun as they go around their orbit. So do they fall the same way? Is there a difference in acceleration of the moon versus the Earth falling towards the sun? And they can say no, because they've got these different measurements, and so they can put a limit on how much the gravity of the Earth could be affecting how the Earth falls. And that limit is great. It's a very sensitive test. But unfortunately, the Earth gravity holding the Earth together is actually not that much. The Earth's gravity is not very strong by astronomical standards. The binding energy holding the Earth together, once you divide it by c squared to get a mass, you get a billionth of the Earth's mass is binding energy. So that limits how good a test these folks can do, even if they've got these very precise measurements. On the other hand, neutron stars are so massive and so compact, the gravity holding them together is like 10% of their mass, minus 10%, is like 10% of their mass. So they've got fantastically strong gravity. These are great objects to test it with. So a friend of mine, Weiwei Zhu, looked at a neutron star and a white dwarf that are orbiting each other, and they're falling into our galaxy. And so you can ask, well, do they experience different accelerations? The neutron star has this tremendous gravity. If ever it was going to show up, it should show up here. Unfortunately, the galaxy is a very gentle kind of gravity, and so he's limited by the weak gravity of the galaxy. We have a system where we've got a pulsar for our test body, so nice strong gravity inside the object. And there's a third body, like the Earth-Moon-Sun system, pulling on the two close together objects. So we have a best of both worlds system. And this is a pulsar. This is one of those stellar remnants. And it's a pulsar in a triple system. So there's a pulsar and a white dwarf orbiting each other every 1.6 days. That has to have survived this widowing process. And in fact, that inner binary that goes around every 1.6 days, like the Earth and the Moon, is orbited, or is in an orbit with another white dwarf further away that orbits every 327 days, like the Earth and Moon going around the Sun. So you have this sort of triple system that's left over after this widowing process. And the pulsar is actually a very fast pulsar. It spins 300 times a second. And it's a little bit miraculous that such a thing could happen, and we have these extremely complicated, two different ideas of how it formed, both extremely complicated. I will not go into detail, except to say that if you take two stars and you want to tear them apart, you actually have to lift them apart. You have to put energy in. But if you have three stars, you can kick one out by stealing energy, by letting from the other two, by bringing them closer together. So triples are actually extremely delicate. It's easy to break up a triple. And so this is actually an astonishing system where not just a binary survived the widowing process, but actually the whole triple survived the widowing process, and it's kind of miraculous. And if we can't imagine a sensible way for them to have formed, that's just a failure of our imagination, because it's out there. We found it. So, but it's also important that it's a neutron star. I mean, neutron stars are great. They've got nice, strong gravity, but they have another wonderful feature. They put out radio waves. It's like the Earth has aurora over its poles. Well, over the magnetic poles of the neutron star, there are big sparks. And so as it goes round, the sparks sweep past us once every time it turns. And that's repeatable. If I point Arecibo at this object, and I average over 20 minutes worth of rotations, what I see will be exactly this pattern of bleeps coming out of it, over and over and over again. And depending on how good my prediction was, it'll always be this shape, but it might be early or it might be late, depending on my prediction. And I can measure whether it's early or late to the nearest microsecond, because this is only 2.7 milliseconds here. So I can measure very accurately whether the pulses are arriving early or late. What's more, we've been observing this for 6 years, and we are able to count every rotation of the neutron star. So I can say that rotation number 56,528,015,489 happened on May 17th, 2017, May 14th, 1951, 17.9973500 UTC. This is why we get such precise measurements. We are great at measuring time, and we are able to measure these times very exactly. So for example, if I wanted to know how fast this was rotating, I would take that 6-year time span, which I know to the microsecond. I would divide it by 56 billion whatever, and I would have the spin period of the pulsar to 13 decimal places. Now, nobody actually cares how fast it's spinning to the 13th decimal place, but there's another way pulses can be early or late than the pulsar spinning too fast. They can be early or late if the pulsar is further from us or nearer to us. If it's 300 meters further away, the pulse will arrive a microsecond later. If it's 300 meters closer, the pulse will arrive a microsecond earlier. So every one of these measurements we take are how far away is the pulsar to the nearest 300 meters. We have these extremely precise measurements of the pulsar's orbit. This is fantastic. It's these measurements of the orbit that let us test the strong equivalence principle. We can ask if the orbit is distorted by the pulsar's intense gravity. And to do this, we've got observations. We've got something like 800 observations, 1,200 hours on Sky, with Arecibo, Green Bank, and the Dutch Westerbork Synthesis Radio Telescope, 3 of the best radio telescopes in the world. This is a fantastic data set. And as I say, in 20 minutes, we can measure the distance to 1 microsecond. So we have an awful lot of precision measurements of the orbit. Now, I won't go into detail here, but modeling the orbit is complicated. There's no simple formula. We have to simulate, and we have to do a bazillion simulations. But fortunately, that sounds like a lot of work, but it's a lot of work for computers, and I'm happy letting computers do all the heavy lifting. So we are able to twiddle the orbital parameters. We're able to twiddle the parameters and find what matches our data best and get very precise measurements of the orbit. For example, we know the pulsar weighs 1.4359 times the mass of our sun. So we have these precise measurements of the orbit. So we are able to ask, is this orbit distorted by Einstein being wrong? Is this orbit distorted because the pulsar is accelerated differently than the white dwarf by the gravity of the outer companion? Just like the lunar laser ranging people asked, is the Earth accelerated differently from the moon by the gravity of the sun? And our answer is no, actually. The pulsar and the white dwarf accelerate the same. The difference in acceleration between the pulsar and the white dwarf is no more than 3 parts in a million. Now, I've been throwing big and small numbers at you the whole time, but I'll point out that we don't know the value of big G, Newton's gravitational constant, to 3 parts in a million. This is a very precise differential measurement. And for comparison, if we want to compare our result to the lunar laser ranging, well, we're using different test objects. They're using the Earth as their test object, and we're using the pulsar as our test object. So you have to sort of divide by how strong the effect would be. But the lunar laser ranging, they've got 10 to the minus 13 level acceleration limits. But then they have to divide that by the 10 to the minus 9 level effect on the Earth, 10 to the minus 9 level gravitational binding of the Earth. So they get a 10 to the minus 4 level constraint on theory. We have only a 10 to the minus 6 level acceleration constraint, but our test body is 10% of its mass is this binding energy we're interested in. So you'll divide 10 to the minus 6 by 10 to the minus 1, and you get a 10 to the minus 5 level constraint. So we have about a factor of 10 improvement on lunar laser ranging. Did I mention they have 35 years of centimeter scale measurements and sent a man to the moon to get that set up? We have a couple years of postdoc labor here. We have improved on the lunar laser ranging result. And in fact, we've also improved on, I won't go into any detail here, quite a variety of other tests of this aspect of general relativity, and in fact of other aspects of general relativity. In many ways, we have the most sensitive test of Einstein's theory of gravity to date. It passes, and we improve quite substantially on all other existing ones. And I should say, before I finish, that this is not because I am clever. This is because we have this wonderful natural laboratory. We've found a system that miraculously survived the Wittering process, where there is a millisecond pulsar and a white dwarf orbited by another white dwarf. There's a millisecond pulsar in a stellar triple system. There's only one currently known, and it's fantastic that we found it. That's what makes this possible. Thank you.